Welcome back, everyone. Today, we're diving into a topic that honestly gives a lot of people cold sweats: matrix mechanics. We're going to completely demystify how these grids of numbers multiply, and we're going to tackle the really weird concept of matrix division. Let's jump right into the rules of linear algebra. To kick things off, let's look at a super simple question. If I tell you 3 times x equals 6, your brain probably does the math instantly, right? You just know x is 2. It's basic arithmetic. You're just dividing 6 by 3. But what happens if these aren't just single numbers? What if they're entire grids packed with numbers, matrices? Well, your natural instinct is probably to treat matrices exactly like regular numbers and just try to divide them. And that, my friends, is where the first huge mistake happens. Treating a matrix like it's just a regular number? Absolute trap.
To avoid falling into that trap, here is our roadmap for today. We'll start with a strange matrix product, then look at the trap of order. From there, we'll shatter the illusion of matrix division, check out the role of the determinant, and finally, we'll calculate the inverse matrix and look at some advanced methods.
Section 1. The strange matrix product.
Okay, it's time to break the illusion that linear algebra is just a supersized version of basic math. In ordinary math, you really want to just multiply coefficient by coefficient, right? Like if you have a 2 in the top left of matrix A and a 3 in the top left of matrix B, it's super tempting to just write 6 in the result matrix. But as the math prep course we looked at explicitly warns, matrix multiplication is absolutely not done coefficient by coefficient. Instead, it follows this fascinating, kind of weird rule called row by column.
Now, let's be super precise here. There actually is one very specific case in math where you do multiply matrices element by element. It's called the Hadamard product. But, and this is a massive but, you need to understand this is an absolute exception. It is not the standard rule of linear algebra. It's not what you use to solve systems of equations, or transform data, or run AI models. So for our purposes, put that out of your mind.
So here is the real way you do a standard matrix product. It's almost like a dance. To find just one single number in your final matrix, let's say the one at row I and column J, you have to take the entire row I from the first matrix and match it up with the entire column J of the second matrix. You multiply those matching elements one by one, and then you add all those little products together. And here's the catch. For this lock and key operation to even be mathematically possible, the number of columns in the first matrix literally has to match the number of rows in the second. If they don't match, the dance doesn't work.
As you can imagine, this mental gymnastics takes a lot of focus. In fact, the course Legendre group gives a really stark warning about this. They note that matrix calculations are often a huge source of careless errors, which can cost students dearly in engineering exams. And it makes total sense, right? With all these cross multiplications and additions going on, you forget one tiny minus sign and boom, your entire result is completely wrong. So seriously, take your time when you're doing these by hand.
Section 2. The trap of order. A times B is not equal to B times A. Now, in our everyday lives, 4 times 5 or 5 times 4, it's always 20. That's commutativity. But matrices? Generally speaking, they do not commute. The order in which you multiply them drastically changes the result. In fact, sometimes A times B is completely doable, but B times A is literally mathematically impossible because of that row and column matching rule we just talked about. It's wild.
Section 3. The illusion of division.
Okay, remember our opening equation? Here is the absolute core takeaway for today. You cannot divide matrices. It's just not a thing. You can't stick one matrix on top of a fraction bar and put another one underneath. Instead, linear algebra uses a much more elegant workaround, multiplying by the inverse. So instead of dividing by A, we multiply by the inverse matrix of A, which is written as A to the power of -1. And here's the beautiful part. When a matrix meets its inverse, they cancel each other out perfectly to leave us with I, the identity matrix. Think of the identity matrix as the number 1 in the matrix world. It's got ones running down the diagonal and zeros everywhere else.
Section 4. The role of the determinant.
Now, you can't just invert any matrix you want. There's a gatekeeper, and it's called the determinant. It's a single numerical value that you can calculate from a square matrix, and its rule is ruthless. If a matrix's determinant is exactly 0, you cannot invert it. Period. End of story. It has no inverse. So before you even waste your time trying to find an inverse matrix, you absolutely have to put it through the determinant test.
Section 5. Calculating the inverse matrix. So, let's say our matrix passes the test. How do we actually build its inverse? Well, Zeid Benghazi's course breaks it down into a clear 4-step recipe. Step 1, you calculate that determinant. Step 2, you transpose the matrix, which basically means flipping it so the rows become columns. Step 3 is finding the cofactors, which involves calculating smaller subdeterminants and applying an alternating sign based on the formula -1 to the power of I plus j. And honestly, applying that alternating sign is where pretty much everyone messes up, so be careful there. Finally, step 4, you divide this brand new matrix by your original determinant. And boom, you've got your inverse matrix. Section 6. Advanced Methods, Gauss and LU.
Okay, but calculating all those cofactors by hand for a really big matrix, total nightmare. That's where the Gauss pivot algorithm comes in, as highlighted by the University of Toulouse. This method is seriously like magic. In step 1, you set up your matrix A right next to the identity matrix I. Then in step 2, you apply logical operations across the rows. You add, subtract, and multiply the rows together, chipping away at the left side. The goal, you want matrix A to slowly transform into the identity matrix. And then the magic happens in step 3. Once the left side becomes the identity, the right side, which has been going through the exact same operations, has magically transformed into your inverse matrix.
There's another brilliant approach highlighted in the Helm resource called LU decomposition. The core idea here is to shatter your matrix A into two simpler matrices, an L matrix, which is lower triangular, and a U matrix, which is upper triangular. Why bother doing this? Because solving an equation with a triangular matrix is incredibly fast and easy. You just use simple substitution. So instead of wrestling with one massively complex system, you're solving two super simple systems, one right after the other. It's a lifesaver, especially when you're programming this for computers.
To wrap up our explainer today, I want to leave you with something to really think about. If multiplying by an inverse matrix lets you basically undo a mathematical transformation, if it lets you rewind time on a calculation, so to speak, what does it mean physically or geometrically when a matrix has a determinant of 0? What does it mean when you literally cannot invert it? Well, it means that during that transformation, information was destroyed. It was flattened out and lost forever. Pretty mind-bending, right? Thanks so much for joining me to unpack all this. Keep exploring, keep questioning, and I'll see you next time as we break down another fascinating topic together.